In this video I want to explain what permutations are and how to count them, and the idea of a factorial is going to be something that helps us to simplify that process a little bit. So first of all, what is a permutation? Well, a permutation is an ordered arrangement of objects. A permutation is an ordered arrangement of objects. What do we mean by an ordered arrangement? Well, let me give you an example. So the ordered arrangement ABC is, let's say, a different permutation to the ordered arrangement BCA, even though it's the same selection. Though it is the same selection of three letters. Now you might recall that we call that a combination, so a selection in maths is called a combination, but for now we'll just call it a selection. So a permutation is an ordered arrangement. Alright, so let's think a little bit more about how we can count those. Let's say, e.g., how many permutations of the letters P, Q, and R are possible? Now maybe you know that straight away because it's not too difficult to sort of think of those straight away. If we were going to list them, which we'd probably only do in a very simple case, and this one certainly is a fairly simple case, let's list them all off. So if we're starting with P, we can have P, Q, R, or P, R, Q. If we were starting with the Q first, we could have Q, P, R, or Q, R, P. And if we had the R first, what could we have? R, P, Q, or RQP. Hopefully those are all different, but there's our 6 possible permutations or arrangements. What about using the multiplication principle? Because this is the way that we'd probably be more likely to do it, and certainly if it was a kind of bigger problem than this, we'd use our multiplication principle. So we could do this in different ways. One of the ways that we could try and visualize it is to think of filling in the spaces. So the things that we need to do are pick a first letter, choose a second letter, and choose the third letter. And so when we say, well, how many ways are there of picking the first letter in the permutation or the arrangement? There's 3. We can choose P, Q, or R. Now after we've chosen one of those, there's only going to be 2 remaining letters. So in the second choice, or the second position, there are 2 letters remaining, and by the time we've chosen 2 of them, there's only going to be 1 left. Now, obviously, depending what was chosen first and second will make a difference to what that last one is, but there'll always only be 1 option remaining for the last choice. And so using our multiplication principle, we can say 3 times 2 times 1, because remember, our multiplication principle is an AND situation, so there's 3 ways of choosing the first, and 2 ways of choosing the second, and 1 way of choosing the third letter. So 3 times 2 times 1 is equal to 6 permutations. Just put an abbreviated form there. Okay, 6 permutations. What if we were going to try and generalize that? So let's try and generalize this, and let's think about generalizing the number of permutations. In fact, let me write this as a statement. So generalizing here, we could say the number of permutations of n objects. Well, for 3 objects, it was 3 times 2 times 1. So for n objects, it's going to be n times n minus 1 times n minus 2, and so on, all the way back to 1. And that, in shorthand way, we can write as n exclamation mark, which is pronounced or read as or said as n factorial. So let's just write down here where n factorial is n times n minus 1 times n minus 2 times all the way back to 1. Alright, so for 3 objects it was 3 times 2 times 1. For 8 objects it would be 8 times 7 times 6 times 5, etc. back to 1. So for n objects it's n factorial. Now just a couple other things about our factorial notation, or our sort of factorial operation. It would be helpful to note, this is a very important definition, that 0 factorial is defined as being equal to 1, and that will be fairly important. We'll sort of see that come out in a couple of things, but just for now 0 factorial is defined as being 1. What's also helpful is to note that n factorial could be written as n times n take 1 factorial. Can we see that that's the case? So if I look at the way that n factorial is defined here, and I take out the factor of n, then the remaining factor here is n take 1 factorial. If I took out n times n take 1, I'd have a remaining factor of n minus 2 factorial. So I could write it as n times n minus 1 times n take 2 factorial. And, so on, etc. So let me show a quick example of where we might use that. For example, can we evaluate, and you do have a factorial button on your calculator, so if it's tech active you can do this on your calculator, but what about tech free? I'm trying to evaluate something like that expression there, 13 factorial divided by 2 factorial times 11 factorial. Alright, well let's think about 13 factorial is 13 times 12 times 11 all the way back to 1, so I could write it as 13 times 12 times 11 factorial. Now 2 factorial is actually equal to 2, isn't it? Because 2 times 1 is just 2, so we're going to get 2 times 11 factorial, and the usefulness of writing the numerator in that way is that now I can cancel out the common factor of 11 factorial, and I've just got 13 times 12 divided by 2, which I guess I could write as 13 times 6, and what's that, 78? I think that's 78, isn't it? So there's a way that we could use that, and when we're doing it sort of algebraically, that might be even more useful. Now let's extend this just a little bit further in terms of counting permutations. So let's think of another example. Let's say, how many permutations or arrangements? So permutations of 3 letters are possible when chosen from, let's say, 8 letters. So, maybe the letters A, B, C, D, E, F, G, H. Is that right? So the first 8 letters of the alphabet. If we've got 8 letters of the alphabet to choose from, and we're trying to choose 3 of them, so again, we could think of choosing our first letter, our second letter, and our third letter. So if I've got A, B, C, D, E, F, G, H, the first letter I choose, there's 8 possibilities to choose from. But now for the second letter, 1 has already gone, there's only 7 left to choose from. And the third letter, 2 out of the 8 are gone, so there's only 6 options left to choose from. So my number of permutations would be 8 times 7 times 6 using the multiplication principle. 8 times 7 is 56, 650 is 336. Alright, so 336 different permutations are possible. Now what I'm going to do is use permutation notation here. and also try and generalize it a little bit. So using permutation notation, that problem would be expressed as 8p3. Okay, the number of permutations of 3 things chosen from 8 would be written as 8p3. And we could write this using factorials in the following way. So by recognizing that 8 times 7 times 6 is in fact equal to 8 times 7 times 6 times 5 times 4. So I'm just writing it out here so that we can express it using permutations, using factorials rather. So if I write that, then on the denominator I'm going to need 5 times 4 times 3 times 2 times 1. And hopefully you look at that and think, well, you're making it more complex, and yes I am, but the important thing is that these factors here, the 5 times 4 times 3 times 2 times 1, and these ones here cancel each other out to leave me with what I started with, but importantly they allow me now to write this in terms of factorials. So now it's 8 factorial over 5 factorial, but even more kind of significantly I can write it in terms of the numbers 8 and 3 by recognizing that the denominator is in fact 8 minus 3 factorial. So 8p3, the number of permutations of 3 things chosen from 8, can be calculated using the formula 8 factorial over 8 take 3 factorial. And so we can generalize that. Let me just use a little bit more space here and say, in general, the number of permutations of R objects chosen from N objects is NPR. It's the notation for it, and it's equal to N factorial over N take R factorial. Now that's a result that we need to be able to use. We need to know it. It is on your formula sheet, so you don't actually have to remember it, but it's one that we definitely need to be able to work with. And there it is as it appears on the formula sheet. Note that it actually sort of gives you an expanded definition of that too, but I think it's probably easier just to really use this first part of it here, and then to simplify with our sort of strategies that we were talking about here and in this example up here. So sometimes we can do these calculations without our calculator, but your calculator definitely has an NPR function as well.